So today comes like the stuff that will make you really actual chemistry students. Now you'll know real stuff. So today we're going to talk about stoichiometry, which is a way that you relate quantities of substances using a balanced chemical equation. The most important concept you'll learn all year. You'll do this over and over every module. If you don't master module 6, it's going to go downhill. So super important. Not that complicated. I mean, the same thing pretty much happens in every problem. You've just got to be able to do it consistently without looking. And so make sure you practice. Make sure you do the extra practice problems. Like, you cannot get enough practice on this. It needs to be fully mastered. So, other than stoichiometry, really the only thing that you had this week was Gay-Lussac's law, which says that you can relate quantities of gas in volume instead of just in moles. So, if we write a couple of equations. Alright, so what if I want to combust some methane? How would I do that with the complete combustion of methane? Okay, so Micah.
CH4 plus O2 should produce CO2 and H2O.
Okay. So complete combustion always uses oxygen from the air, always produces carbon dioxide and water. So now is when phase symbols start to become important when you're talking about Gay-Lussac's law. Why is that? Kristen? When you're talking about Gay-Lussac's law, why is knowing the phase really important? It only applies to gases. So, I'll tell you, because that's mysterious. Methane's a gas, that's natural gas, when they talk about natural gas pipeline and this and that. And how about oxygen?
Gas.
Gas, always a gas when we're talking about combustion. How about carbon dioxide and water when they're products of combustion? Those are always gases when they're products of combustion. So, could we use Gay-Lussac's law to relate quantities of these items?
Yes.
Yes. Is it balanced?
No, there should be 2's in front of oxygen and H2O.
Alright, so now that it's balanced, we could use Gay-Lussac's law. So if I say I have 1 molecule of methane, and I put it into the balanced equation, how many molecules of oxygen would I need for every 1 molecule of methane?
Twice that.
Twice the amount, because there's a coefficient of 1 there and a coefficient of 2 there. So what if I say I have 2 moles of oxygen to combust? How many moles of methane could that combust? Half of that. So for every 2 moles of oxygen I can burn up 1 mole of methane. But since everything in this equation is a gas, Gay-Lussac's law also applies. So I could just as easily say, I've got a liter of methane, I'll need 2 liters of oxygen to produce 1 liter of carbon dioxide and 2 liters of water vapor. So that applies. Now what if not everything is a gas? So what if we have, let's see, well, propane, methane, C3H8. Propane comes, it's a liquid when you buy it in the tanks, it's all pressurized. So let's say we've got liquid propane. We want to combust that. Yes. So if we combust that, how would I write that equation, Saul?
Plus O2, and that would be a gas. And then combustion always just turns out to be a gas.
And how would I balance? So if I want to balance that, what do I need to do? Where would you start if you're balancing that?
You'd have to double the carbon and hydrogen on the left side.
This one?
Yeah.
Alright, and then a 2 there.
Then I think 7 oxygen. And that will make 6 6 carbon dioxide. And, oh, you know, I don't think I put enough oxygen.
Well, you've got this one left, so. How many hydrogens do you have?
Or no, I think I do. And that would make 4 water.
All right, I'm gonna really think about this because you're faster than I am. Hold on. Okay, so 2 times 3 is 6 carbon, 6 carbon. It's good. I would start with carbon in that one. I leave hydrogen and oxygen to last almost always as a rule. Hydrogen, I've got 2 times 8, that's 16. Only 8 here, so that's not enough. So if I have 16 over here,
Oh, that's right, I forgot
put an
about
8
that.
there, that's 16. Now oxygen, 14.
Oh, we just need more oxygen.
Might need more oxygen. So I've got 8 and 12, that's 20.
So we need 10.
Okay, then here's the last thing. Oh, having a 10 next to oxygen is like 2 O's. Then look through your coefficients. 2, 10, 8, and 6 are all even. So when that happens, what do?
You can divide by 2.
Yep. So we'll just leave that one a 2 or 1. That one's a 5. We're right about the 4. And a 3. So are we balanced now? 8. Okay, good. All right. So now that's the combustion of propane. So how can we use Gay-Lussac's law in this? Could I say for every 1 liter of propane, I need 5 liters of oxygen?
No.
No, because Gay-Lussac's law does not work for a liquid. So you can't say that. Could I say that for every 5 liters of oxygen gas I burn up, I'm going to produce 4 liters of water vapor? Yes, I could say that because they are both gases. So it's not like you can't apply Gay-Lussac's law when there is a liquid or a solid or aqueous component of the equation, but you can only apply it to those reactants and products that are gases.
But kind of made it sound like it wouldn't apply to the entire equation.
Yes.
So I was a little confused. And
That's
I'm
the
like,
only
oh,
reason I
yes.
do this. Because the book was just a little bit like hard to understand there, I thought, but I'm glad someone else agrees. Okay, so Gay-Lussac's law just says you can relate the balance equation's coefficients to gases in terms of volume in liters or milliliters or something. But of course not liquid, solid, or aqueous components of the equation. So there's that. But that's all we need to say about that. The problems will go over it a little bit. And don't forget that you can always apply every coefficient to moles. So I could still say about this equation, 1 mole of propane could be combusted to produce how much carbon dioxide? 3 moles of carbon dioxide. So moles always work for everything. Now, here's the key point about this chapter. Could I say that 1 gram of propane will produce 5 grams of oxygen?
No.
No. Here's like rule number 1, biggest rule ever in chemistry. Grams, if you have grams of one thing in the balanced equation, you can find out every single thing about the whole equation, but only if you relate moles to moles. So you just use your periodic table to convert grams to moles. Okay, so then if I knew grams of propane, I can convert that to moles by finding molar mass, right? Add up carbon's atomic mass is 12, hydrogen's is 1.01. If I added up 3 carbons and 8 hydrogens to find the molar mass, convert the amount of grams of propane to moles of propane, then I use the coefficients to relate moles of one reactant or product to moles of another reactant or product. Then I know moles of something else, and I can use its molar mass to convert it to grams. So the key point for next week's math, and this week's lab kind of, is you have to be able to convert grams to moles, and then you can convert to moles of anything else, and then to grams of that. But you must go through moles to relate masses. You must have gases to relate volume for the balanced equation. So that's really everything I have to say. Now the big decision. Let's do review questions and practice problems and then the lab, I think. hate the risk of running out of time with the lab, but the lab math is a little harder, so I'd like to make sure we're all ready. All right, so can go here. That is scary. Okay. So let's look at review questions. And we did five review questions this week? Okay. All right, let's start over here with Kristen. Define stoichiometry and explain why it's a useful tool.
Stoichiometry is relating the quantities of substances in chemical equation. And it's useful because you can use it to find the quantity of things and substance in equation to one quantity.
Good. So if you know one thing about any one part of the equation, you can find the quantities of the other. But you have to go through what? Can you use mass to do it? No, what do you have to use? Moles. Jen, aim the camera at people when you talk so that we're not looking at you. All right, Maddie, explain what a limiting reactant is and why it's important in stoichiometry.
A limiting reactant is the reactant in a chemical reaction where once it runs out, the reaction will stop. This is important because it can be used to stop a reaction.
Perfect. So, with limiting reactant, that's what our lab activity will be about this week. It's what it'll also be about next week. It's very important. So, if you get a problem and they give you information about multiple chemicals, and you have to figure out, well, which information is important in this problem, you have to use the limiting reactant to do all the math, because it's the one that runs out first. It stops the reaction. If you use the excess chemical to do the math, you're going to get the wrong answer. So you always use the quantity of the limiting reactant to do all your math having to do with the equation. Should you make your most expensive or least expensive chemical your limiting reactant? Most expensive chemical, your limiting reactant. Your professors will not be pleased if you use the, gold nitrate as your excess reactant, obviously. You definitely want to make sure your expensive stuff is the limiting reactant. You don't want to waste the expensive stuff. Dump in plenty of the cheap stuff. Now, Dr. Weil made money in college doing that. I think he said in something I read that he would take the waste jug and reclaim all the silver compounds out of it and plate like people's jewelry and silverware and stuff with silver from the waste jar, using electrolysis basically, and then sell it for, or charge people money for the waste silver that he could reclaim out of the waste jar because people weren't careful to use that as the limiting reactant sometimes. So, just don't waste the lab's money when you choose your limiting reactant carefully. All right, Lily, a chemist, this is 3. A chemist experiments with the following reaction. So probably you almost don't know how to name any of this stuff. So I'm going to say the equation has 14 moles of HCl, which is hydrochloric acid, plus that K2Cr2O7, that's potassium dichromate, which only a few modules from now you will know. Potassium dichromate. Dichromates have beautiful colors. Very interesting ionic compounds. And when you mix those two things, you produce, well, you can name that one. So 2KCl, what's KCl?
Potassium chloride.
Potassium chloride, no prefixes because that's ionic, plus CrCl3.
And chromium trichloride.
Well, chromium's a metal, so it's ionic, so just chromium chloride. And it would be chromium 3 chloride because chromium can have different states, which I haven't taught you yet, but just so you know. And then what are the other two products?
Chloride and water.
Chlorine and water. Because Cl2, since chlorine is a homonuclear diatomic, that's its elemental form, so that's the element chlorine, even though it looks like a molecule. So if the chemist adds 15 moles of hydrochloric acid to 1 mole of potassium dichromate, what is the limiting reactant?
Just a second.
That thing, the
that.
potassium dichromate. So how could you tell that?
Because there's less of it, so wow.
Okay, so if you compare, it tells you have 15 moles of hydrochloric acid. In the balanced equation, how many do you need? 14. And then 1 mole of potassium dichromate. In the balanced equation, you need 1 mole. So you have more moles of hydrochloric acid than you need in the balanced equation, and the same amount of moles of potassium dichromate as you need. So hydrochloric acid is the excess. Potassium dichromate is limiting, which is a good choice because it's a more expensive thing. So they got that one right. Good. All right, Saul. State Gay-Lussac's law and explain how it's used.
I don't know the exact like word for word,
That's
but
okay.
it's,
Just give us your own words.
it's basically says that the coefficients of the stoichiometry equation can the volume can be related to the number of moles. So if you have 3 moles, then you could say 3 liters, and then convert all the like the balanced equation from moles to liters, and it'll work.
Now, that's not quite it. That's something you don't want to do. You can't say, because I have 5 moles, I have 5 liters. That's not true. What you can say is, if I use 5 liters, I'll get 4 liters of this and 3 liters of that. But if you're going to use moles, use moles. If you're going to use liters, use liters. But don't try to relate moles to liters with Gay-Lussac's law. Okay? So just, you can relate liters to liters to liters with all the gases in an equation. But if you need to use something else, or you want to know about moles or grams, then you need to use moles. Don't use liters. But gases are just easier to measure in liters, so you can just catch the contents of your reaction. If it's a gas, measure how many liters that is, and then say, I know how many liters of everything else that is a gas, or was a gas. Which is essentially what we're going to do today in the lab. So only if you're just doing gases, just do gases. If you need to do moles, then you need to do moles the normal way. So yeah, that actually isn't something I thought to tell you, so I'm glad that came up. All right, do we do number 5? 5, yes. Jenny. Main camera at Selby. She said no. A chemist wants to perform the following reaction. So that CaCO3 is calcium carbonate plus 2H2 or HCl, which is hydrochloric acid in a gaseous form. Lots of fun there. And that gives you CaCl2. What's that stuff? Jen? CaCl2?
I don't want to answer things.
Oh.
Okay.
What's Ca? No. Liam, helper.
Calcium chloride.
Calcium chloride. C is calcium. It's ionic because calcium's a metal, so you just put the IDE ending, no prefixes. Calcium chloride. And then what are the other 2 products, Jen?
Water and carbon dioxide.
Tell me real loud. So calcium chloride, carbon dioxide, and
Water.
Okay, so if you look at the phases there, you've got solids, you've got gases, you've got an aqueous thing, you've got a liquid. What substances could you use Gay-Lussac's law to relate to one another in volume?
The 2HCl and carbon dioxide.
Those are the only 2 gases, so yes. All right. Now, let's take a look at practice problems, and we did 4. All right. So, Liam. Aim camera. Actually, Liam's going to get up and write, probably.
Wonderful.
And you're lucky because the balanced equation's already up there. We just luckily used that. So, this is the combustion of propane. When 2.13 moles of propane burn in excess oxygen, how many moles of carbon dioxide will be formed? Assume complete combustion.
I need to see the book.
Oh,
I cannot keep that in my head.
no. You don't look like a best person. number 1.
Okay.
So you've got a balanced equation already, which is the first step.
Cool. Okay. So then, you're gonna try to figure out how much CO2 will be formed.
Yes.
So we take.
Oh, just throw it on the floor. 5 markers. Note to self.
2.13 moles of C3H8. We've got 1 over 3.
Make sure you cancel, like, make sure you keep the chemical and the thing so that you cancel C3H8. Oh, you did. Okay, good.
Error.
Okay.
Story of that.
Should give us 6.39.
Good. So notice he considered significant figures. His data had 3 significant figures. He kept 3 in the answer. He used the coefficients in the balanced equation to relate moles of carbon dioxide to moles of propane. So that's perfect. He kept his chemicals in there. If you want to zoom in on the board so that our absent folks can see.
It doesn't zoom in anymore.
It won't zoom in anymore.
Why do I buy these new cameras?
They won't zoom. Oh, and the glare is really bad too. Oh, I gotta get curtains. New markers and curtains. Ooh, ooh, it almost worked. Okay, if you tip it that way.
Poster board to block the
Ooh,
sun.
good plan.
Okay, maybe that didn't work. All right.
Now it's.
I can hold it up.
Yeah, it's just going to hit right there, isn't it? Maybe we should have hung the periodic table in the window. Okay, so we have moles of propane canceled here. We get moles of carbon dioxide in our answer. We always have right number of significant figures, a unit, and the chemical that we have. So, important way to write your answer.
Yes.
So, Grace. Oh, you get the wrong one here. So silver tarnishes when exposed to oxygen and dihydrogen monosulfide. The chemical reaction is as follows, which I'll put up there for you, and then you can come up and do the problem. So, hopefully the green one. Okay, so we've got 4 Ag, which is silver, and that's a solid, of course, plus 2 dihydrogen sulfide. So is that ionic or covalent, Grace? Covalent, because hydrogen is non-metal and sulfur is a non-metal. So dihydrogen sulfide needs those prefixes. Plus oxygen from the air gives us 2 silver sulfides plus 2 liquid waters. All right. So we have 2 gases in that. So if we needed to relate volume and gases, we could use that and oxygen, but we don't. So it says here, every household has some dihydrogen sulfide in the air, dihydrogen monosulfide, because the second one, when it's a mono, needs a prefix. And it smells like rotting eggs. And usually there's only a small quantity in the air, so it's almost always a limiting reactant. So I usually underline that limiting reactant to make sure I remember to only use it for the math. So if a silver spoon has 0.0012 moles of tarnish on it, how many moles of dihydrogen monosulfide was it exposed to? So can we go up and write?
We have 4 minutes left on.
4 minutes. Maybe we can get through this problem. Oh, batteries on the wall, please charge quickly.
It's the SD card, like the memory.
And the memory only has X amount of video for
I have a
recording.
16 gig chip in there.
You can delete stuff. I don't know.
It was
Maybe take away
empty.
too many pictures, I don't know.
Oh, very frustrating.
Maybe
it should only be like
more
2,000
limited with
pictures.
the rest of the memory.
Well, I don't have anything on there. I delete it every week.
Are you able to change the frames per second if you're recording that?
Maybe you are.
I don't think I would.
And maybe you are able to look at my camera later. Because I don't know
Just take
anything.
over the-
Is the air conditioning working, speaking of?
The-
The lab today really needs a normal temperature, not 80.
it says 70 degrees Fahrenheit.
Remove sweater. Okay, so Grace has put this up for us. So she started out with what we know. Moles is a limiting reactant. So we've got 0.0012 moles of silver sulfide. She compared moles of silver sulfide in a balanced equation to moles of tarnish. Moles of dihydrogen monosulfide to moles of tarnish, which is the silver sulfide. They both have a coefficient of 2, so the actual number didn't change, but she still did the conversion. So why did you still do the conversion when you're essentially multiplying by 1? There's a real reason. Well, you had to cancel out the unit here, essentially, so the silver sulfide, and get the dihydrogen monosulfide. So you have to do that, so you end up canceling here and getting the correct chemical there. So it's still important to show your work, even though you can see that it's really, they're going to be equal amounts. You still have to convert from one chemical to the other using the balanced equation.
I have a question. Is that what makes silver turn black?
Yep. If your mother makes you scrub your silverware every Thanksgiving, before the company comes, you scrub all that tarnish off, this is why. So, yep. I don't do that right. My mother did, though. I had to do that. All right, so Freon. Brittany, Freon is a useful refrigerant produced in the following reaction. So can you name that first thing? It says 3CCl4 gas. So first thing, ionic or covalent?
That's ionic, right?
It is.
No, it's covalent.
It's covalent because carbon is a nonmetal and chlorine is a nonmetal.
So is it carbon? What's it's chlorine, but I don't.
Tetra?
Tetrachloride.
Yep. So carbon tetrachloride, major cancer-causing, horrible chemical, but great solvent. It is. Plus 2SBF3. What's that?
I forget what SB is.
Anyone? Antimony. And it is there. And then, here we go. So it's barely a metal, although they are literally, since it's right on the line, they're literally calling this antimony trifluoride.
Oh, okay.
So they're naming it as a covalent, even though antimony is here as a metal. So it's not behaving like an ionic, it's behaving like covalent. So that one's really tricky. And then you produce Freon and SbCl3, which, how would you name that?
Okay, so antimony trichloride.
Yes. And you wouldn't know that because you would have to assume that it's ionic and just name it antimony chloride.
So
if you hadn't seen it do that.
all the non-metals close to that? Are all the metals close
No.
to that? Okay.
Usually, like aluminum, you're going to definitely consider always a metal.